It's a great day for Gauss-Bonnet. In this video, we're going to talk about the Euler characteristic of a surface. We're going to prove that the Euler characteristic of the sphere is 2 using this clever charge idea. And then we'll sort of talk about the Gauss-Bonnet theorem because we will have defined all of the components. And then we'll look back at a few of the things I called special cases of the Gauss-Bonnet theorem and see how they fit in. Oh, Murphy's excited. Oh, he doesn't know which way to go. That's okay. All right, let's dig in. All right, welcome to It's a Great Day for Gauss-Bonnet Video 4. So last time we talked about Gaussian curvature and geodesic curvature. So recall, Gaussian curvature is how much a surface is bending at a point. And we had a few examples we want to keep in mind. In the plane, we're flat, so we have 0 Gaussian curvature. At a point on the unit sphere, we're going to have curvature +1, and at this point on the saddle, we would have curvature -1. And geodesic curvature, you can think of geodesic as shortest path between 2 points. And a nice example to keep in mind was this sphere, where a great circle will have geodesic curvature 0, and if we shift it up to this latitude line, we'd have some non-zero geodesic curvature. So we know the left-hand side of the Gauss-Bonnet theorem, we're going to add up the Gaussian curvature on the interior of our manifold and the geodesic curvature on the boundary of our manifold, if our manifold has a boundary. It might not. And then what's left to talk about is this quantity over here. So that's what we're going to talk about today, and that's the Euler characteristic. So much you could say about the Euler characteristic, so we're just going to try to as always, give some intuition and some nice examples to keep in mind. But the interesting thing is this curvature is a local quantity. It's computed at a point, whereas the Euler characteristic is a global quantity. You have to consider the entire surface in order to compute it. So that's some of the power of the theorem, is that you can walk around and make these local calculations, and that tells you global information. And vice versa, if you have this global information, you can say something about the local information. So pretty cool. And then we'll take a look back at some of the special cases. So we have the turning tangent theorem and total curvature idea that we saw in previous videos, and we'll see how they fit into the Gauss-Bonnet theorem. Turns out I'm not being completely honest with you when I write the theorem in this way, so I'll have to correct myself a little bit there. Okay, so the Euler characteristic is a topological invariant, meaning that it doesn't change if we continuously deform our surface. So if I took this torus and sort of stretched it out and shifted the whole way to the right, I didn't change the topology. It's a invariant under homeomorphism. So we're allowed to stretch and bend, but we're not allowed to rip or tear or attach things together. So even if I put some sharp corners on it, that's okay. So we're just a homeomorphism. For most of our examples, we're going to assume we have a triangulated surface, and the Euler characteristic, one way to define it, there are many, is the sum of the vertices minus the edges plus the number of faces. I'll be a little bit reckless. Maybe you'd put absolute value here to denote that I'm not talking about the set of vertices. I'm talking about the number, so being a little loose there. So let's look at some examples. So if we just have this triangle, well, we have 3 vertices, we have 3 edges, and we have 1 face. So we'll do 3 minus 3 plus 1 is equal to 1. So we could say the Euler characteristic of this triangle is 1. And one amazing thing to note is we could triangulate this in a different way. So maybe I add an edge and a vertex, and I split a face here. So now V is equal to 4, E is equal to 5, because we split this edge as well, and F is equal to 2, so we'll get 4 minus 5 plus 2 is also equal to 1. So no matter what the triangulation is, or if I stretch or bend this triangle, this calculation is always going to be 1. So that's kind of amazing. So that's what the Euler characteristic is, or an example of the Euler characteristic. So it's a global property. So let's look at some different objects here. So maybe we have the tetrahedron, so we have these faces, but it's hollow on the inside. So how many vertices do I have? I have 4. I have 1, 2, 3, 4 faces as well, and I have 1, 2, 3, 4, 5, 6 edges. So E is equal to 6. So 4 minus 6 plus 4 is equal to 2. And now we could consider the cube just for another example. So I have 8 vertices. How many edges? Maybe you could count in some clever way. Looks like 12 edges. And how many faces? I believe we have 6 faces if you think about a die. So we'll get 8 minus 12 plus 6 is also equal to 2. And notice that topologically, the tetrahedron and the cube are the same. You might say, hey, wait, that's not a triangulation. Well, I could triangulate each of these faces, and I would add an edge and a face. So I get away with squares in this case. And okay, so both of these are homeomorphic to each other, and they're both homeomorphic to a sphere. Maybe you could see projecting them onto a sphere or something like that. But we got 2 for both of those, so that suggests the following. For any convex polyhedron, V minus E plus F is equal to 2. And this is one of my favorite proofs of all time. I first encountered it on David Epstein's website, and he attributed to Thurston and his book that I'll show a picture of here. Okay, so what we're going to do is we're going to triangulate a sphere or any convex polyhedron. So this is a sphere. I know it. Maybe you can't tell. And we're going to do this in such a way that we have no vertical edges. If we do, we'll just perturb them slightly. And no edges, or the north pole is in the interior of the face, north and south pole. So poles inside a face. Again, if they're not, we'll just perturb our triangulation just a little bit. And what we're going to do is we're going to put these charges on. So we'll put a plus on each face, a minus on each edge, and a plus on each vertex. So I'm just going to do this for one triangle, but you would do this all over. And then what we're going to do is we're going to slam our sphere. So slam it down. And all of our charges are going to move down just a tiny amount in epsilon. So all charges move down just epsilon. And let's look at what happens to each one of these triangles. So we could have 2 different orientations. You could have a vertex up above or just an edge up above. But in either case, we're going to start with plus, minus, 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 plus, plus, plus. And when we shift down, well, our plus inside is going to stay inside. This plus is going to move inside this triangle, this minus inside, this minus inside. These things are all going to exit this triangle and move into a different triangle. And what I'm left with is a sum of 0 charge inside this face, which is nice. And if we consider the opposite orientation, the same thing will happen. Well, not the same thing, but we'll get some nice cancellations. So we'll get plus and minus, and everything else leaves. So this is coming outside, 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 outside. And again, we're left with a plus or minus inside, so they totally cancel. But we have to take special care of the north and south pole. So what's happening at the north pole? Well, our plus is going to remain inside the face, and all of our other charges are going to move outside of this face. So we're just left with 1 plus there. And on the south pole, everything's going to move, the boundary is going to move inside. So we'll get a plus, minus, plus, minus, plus, minus. So at the north pole, we're left with a single plus. And in the south pole, we're left with a single plus after cancellation. So we get 2 pluses and none from any other triangles. So that tells us the Euler characteristic is 2. So therefore, Euler characteristic, I'll call it the sphere, but it's convex polyhedra, is equal to 2. And so that's one of my favorite proofs of all time. It's just so clever using these charges. So let's put our end of proof symbol in there, the Bonnet macaw. Very cool. Okay, so we can use this. The other object we're interested in is the disk. We'll see that come up quite a bit. And we can consider stereographic projection. So stereographic projection shows a homeomorphism between the plane R2 union infinity and S2. So we can see this by, if we position our unit sphere as normal with north pole's coordinate 0, 0, 1, and we shoot a ray from this point through the sphere, we can map that point on the sphere to the point on the plane on this line. And so notice that the equator would get mapped to the unit circle, and the North Pole, or the northern hemisphere, would get mapped outside of the unit circle, and the South Pole would get mapped inside. So how does this help us? Well, we can think of the disk, or any triangulation of the disk, as being on the sphere with one face removed. So disk is sphere minus a single face. And so any triangulation of the disk gives me a triangulation of the sphere with one face removed, and vice versa. So using this reasoning, we removed one face from our triangulation, so we'll get the Euler characteristic of the disk is equal to 1. And we saw that on when we considered the triangle earlier. So we'll certainly see other surfaces, but the sphere and the disk are going to be particularly useful. So we have those two things, which is nice. Okay, so that's all the pieces of the theorem. So let's sort of investigate what this is saying. So maybe even a nicer case with one less term is if we have no boundary. Then we just say, well, if we integrate our Gaussian curvature, we get 2 pi times the Euler characteristic. So that could be on the sphere, or maybe a torus, or a genus G surface. No boundary, so we don't have this extra term. And again, there's this beautiful local to global property where this is saying add up, as you move around, compute the curvature at each point. And if we sum all those things up, that'll tell us something about this global property, the Euler characteristic. I always thought that, if you could convince a flat earther to go around and record enough curvature, maybe you could use the Gauss-Bonnet theorem to convince them that we really are living on the surface of the sphere and not the disk. But maybe that'll be one of my applications. That sounds dangerous, but anyway, it could happen. Maybe it could happen. I don't know. It could happen. All right, if we have a boundary, so maybe something like this, what we're going to do is we're going to add up our geodesic curvature on the boundary. Maybe that's not distinct enough. How about some more? Geodesic curvature here, and we'll add up our Gaussian curvature here, and that'll give us our Euler characteristic. So if we have boundary, we just have to include this extra term with the geodesic curvature. So if we have a disk or something, we're going to look at Gaussian curvature inside, geodesic curvature on the outside, and that'll give us the 2 pi times the Euler characteristic. No matter how we bend or morph this surface, we're always going to get to this constant on the right-hand side, which is somehow amazing. Even if you dented something, you created more positive curvature, but you also created more negative curvature. So there's this beautiful conservation happening. Okay, so that's the theorem. Let's go back and revisit some of our special cases. I was a little bit dishonest because I didn't want to write this third term, but I will now. So what is C here? C is a cusp on the boundary. So if we have a surface that looks something like this, maybe, what are we going to do? Well, we're going to add up our Gaussian curvature inside, our geodesic curvature on the boundary, but we also have to pay these exterior angles. So if I turn here, I call these beta i's in the first video. So If there's a cusp on the boundary, you add in the exterior angle, or pi minus the interior angle. So let's say this is alpha I inside. So certainly that's some curvature that needs to be accounted for. So I didn't include that, but maybe we should have, and we'll see why it comes up in our special cases that we've seen so far. All right, so what did we do? We did this theorem of turning tangents. Let me copy this down. Apologize for scrolling, but anyway, here we go. So where are we? We're in the plane. So what does that tell us? Well, that tells us that our Gaussian curvature is 0. So this term is going to be 0. We have a polygon, which implies straight lines. So let's get an example going. I think it looked something like this. So straight lines polygon, that tells us geodesic curvature is 0. What is our surface then? Our surface is a disk. So we know our Euler characteristic is equal to 1. And there we see our theorem of turning tangents. The sum of the exterior angles is equal to 2 pi, or the sum of the interior angles, since those angles are complementary, we get pi times quantity n minus 2. So this is, just write it in here. So this is equal to sum I equals 1 to n of our beta I. And this is 2 pi times 1, which is, of course, 2 pi. And so our turning tangents theorem can be thought of as a special case of the Gauss-Bonnet theorem. Pretty cool. We also talked about this total curvature idea. Namely, if you have a triangle, a geodesic triangle, on a surface, well, the sum of the angles is going to be pi plus this curvature. So the curvature tells you how much some of the angles of your triangle differ from pi. So where can we see this happening? Well, geodesic triangle, I didn't write that here, but this is a geodesic. So what does that mean? Well, this term is going to go to 0. Our Euler characteristic, well, again, this is homeomorphic to a disk, so chi of t is equal to 1. And then that gives us this total curvature. So we'll have, on the left-hand side, we'll have the integral of our Gaussian curvature, plus if I distribute this sum, I'll get 3 pi minus the sum of our interior angles is equal to 2 pi on the right, and then rearranging, we see our Gaussian curvature over the triangle plus pi is equal to the sum of our interior angles. So again, this total curvature of a triangle, geodesic triangle, is a special case of the Gauss-Bonnet theorem. So pretty cool. All right, so what did we do in this video? We talked about the Euler characteristic as this alternating sum of vertices minus edges plus faces, the number of those things. And we saw that the Euler characteristic of the sphere or convex polyhedra is going to be equal to 2, and the Euler characteristic of the disk is equal to 1. And then we talked about our theorem a little bit. This nice local to global relationship is just so amazing to me. I can't get over it. And then we saw that these things I called special cases in previous videos really were special cases, but we had to account for these cusps on our boundary. Not a big deal. All right, next time we'll dig into a new application. I'm not sure exactly what that'll be, but thanks for tuning in and thanks for watching the entire video. Yeah, leave some feedback or comment. I would really appreciate it. So thanks so much.